Okay, so say that I have a bar, and I know that the cross-section of the bar here at the wall is A0. And I know that on the bar, there is a known distributive loading, Fx of x. So I know the loading, and I know the length of the bar. The length of the bar is simply L. And the thing that I do not know is how the bar is shaped. I have to design. So this is a design problem. I do not know yet what the bar looks like because I have to decide what the bar looks like. So the bar is going to have some shape. Am I deterred by this? No. I just call this cross-section A of x. I don't know what it is, but I can give it a name. Give names to your unknowns. Let's put x going that way. Okay? And let's say that I know. Let's see what I know. I know that the length of the bar, I know that it's made of one material, so I'm not going to mess up with that. One material. E, I know the modulus. I know the area at x equal L. Let's call it A0. And I know the load distribution, Fx of x is equal to B0 times x. So the design part is that I want sigma n of x to be constant. So that's my design criterion. I want to have a bar in which the stress is constant. All right? That means it has the same chance of breaking everywhere. Hopefully of not breaking everywhere, right? So I want sigma n of x constant. I know all this stuff. And so what I want is I want to figure out A of x so that it gives me a constant sigma n, right? So that's my plan. Okie dokie. So what do? I'm not going to start pulling my hair out. I'm just going to go forward. Excellent. No problem. So what is my first step? What did we say was my first step? Who goes first? What do I plot first? Plot the loading. So let's plot the loading. Fx of x. So remember, this whole thing from here to here is L. So if I plot Fx of x, it goes from 0 to L. Well, even I can plot that. B0x. How easy is that? Boom. What is the value here? B0 times L, right? So remember your units. We're going to talk a little bit more about units because when we did all our theory and equations last time, I did not talk enough about units. You want this whole thing to be in what? This is the distributed load. So what are the units for that? You guys are on top of it. I don't need to do any work. Newtons per meter. So if I obtain it multiplied B0 by x, it means that my B0 needs to be in Newton meter square. Okay, so this is not a dimensionless constant. So when I then do B0L, I have the distributed load here, which is going to be Newton per meter. Okay? So one, plot Fx of x. Boom, done. Number two, obtain n of x. Okay, I can do that. So what do I do to obtain n of x? I just take my bar and I do a cut. I cut. And now in this case, this bar There is not like a concentrated load here, a concentrated load here that I need to do different cuts. I can cut at the generic x. Wherever I cut, I'm going to have the same equations. You see that? Because nothing changes along the bar. Everywhere in the bar, there is the same fx of x. So my equations are going to stay the same. All right, so let's make a cut. So I cut at some generic distance x. So when I cut at the generic distance x, I still have, remember, when you take the cut, do not take away your loads. Fx of x is still there, happy on the chunk you keep. Don't toss your loads. Your loads stay. Here, where I tossed away the bar, I need to replace what I tossed with the load that was transmitted to that section. Remember, n of x, you plot it coming out. Okay? N of x goes out from your cut. Okay, so this is my free body diagram. And then you say sum of the forces x must be 0. And that's going to be equal to, see the x goes that way, it's going to be equal to n of x plus the resultant of all this loading. So I have to integrate these loads going from x equals 0 to x equal x. So I have to do the integral from 0 to x of fx of x, which is b0x, in dx. Okay, so that is n of x plus b0 over 2 x prime squared between 0 and x. Now you see how pedantic I am? I always say this is the integral, x prime squared over 2, and I never forget to put my bounds. If I forget to put my bounds, you just tell me, put the bounds. Okay, so put your bounds, and then if I solve that, I get that n of x is equal to minus b0 over 2 x squared, and that 0 gives me 0, so I'm done. Okay? I say give me the bounds because, for instance, if I was integrating, the bar was facing the other way, and my bounds were from L to x, then if this was L, I would get another term here. Do you see? Okie dokie. Yes?
Why is it 0 to x and not L to x?
Because my x starts there. It's just my choice of how I draw the x.
Okay.
I draw the x starting at the end of the bar, so it goes from 0 this time. Okay? Okay. So that's my n of x. I can plot it out, no problem. N of x. And if I put n of x is minus b0 over 2x squared, so I see that for x equal L, it's going to go to b0 L squared over 2, and is negative. It goes like that. I look at this plot, and I ask myself, does my walk the beam work? Yeah, it works. It works because, like here, I have 0 distributed load, which means 0 slope for n. The slope goes from nothing to big. And if f of x is positive, then the derivative, minus that is negative. And you see that the slope goes down. So this one here looks good in terms of dn dx. I like it. So I check to make sure that I don't make mistakes, because man, do I make mistakes. OK, so I got n of x. So after n of x, I have part 3, which is my EA effective of x. And EA effective of x is simply equal to E times my unknown A of x. That's an easy one. Excellent. So number 4, I can get now my epsilon A of x. Epsilon A of x is going to be equal to n of x divided by EA effective of x. So that's equal to minus b0 x squared over 2 divided by E A of x. I keep going like a train. I can't be stopped, like the Energizer Bunny. Sigma n of x is equal to epsilon A of x times E. I multiply that by E, and I get minus B0 x squared over 2 divided by A of x. All right. Now, do I forget the minus sign? No. Notice that the Energizer Bunny could have taken a shortcut. That's my axial load, right? That's my stress. And I find the not surprising result that my stress, because my bar is homogeneous, is simply equal to the axial load divided by the cross-sectional area. And you're thinking, what is she wasting all her time going through epsilon A of x and doing sigma n of x, doing this times that? And I'm doing it because one of the main mistakes that you guys make over and over is when you have a composite bar to simply obtain the stress as the axial load divided by the area. This is correct as long as you only have one material, because you see, everything cancels out. But if the bar is composite, you have to follow this and then put here the E of the material that you want. Okay, so I take the extra step here of doing it that way, even if in this case was not necessary, because now that you're starting to do these problems for the first time, it's better if you take a little longer path, but you know it's safe, rather than the shortcut, because sometimes the shortcut is not right. Okay, so once you've done a few of these and you know what is right and wrong in terms of that, you are smart enough to see this is not a composite bar, you can take the shortcut, you take it. Okay, so what do I do with this now? So this means that my sigma n of x, if I write it simply as, so my sigma n of x is equal to minus B0 over 2 x squared over A of x. And I want this to be constant. Right? So what does that tell you? It means that x squared over A of x must be constant. I know how much constant, an extra n, constant. I know how much x squared over A of x is right here. Because right here, the bar has, the x is at L, and the cross-section is A0. So this must be equal to L squared over A0. So out of that, I get that my A of x is simply equal to A0. So if I bring it up, A0, x squared, x over L squared. So what does my bar look like? It's going to look like a pointy nose, like the cross-sectional area. So that's what it's going to have. See, the area goes at 0 at x equals 0, and then it increases. So if the radius increases linearly, the cross-section goes quadratically, right? So why do I need to have a shape like this? Well, I need to have a shape like that because my fx of x also increases, all right?
How did you get A of x? Was that an equation?
I inverted that. So I took that and I say A of x, bring it up, equal to L squared. I bring it here, oh, sorry, x squared over L squared, and then I bring a 0 up. Right, so just from that. Okay? So in this case, see, I didn't know even what A of x was. I don't care. I still go forward. I get to a final equation. I see what my destination is, and I invert it, and I find what I need. Okay? Let me show you one kind of problems in which you actually need to walk backward like, crabs. So the only problems in which you need to actually walk backwards are, you can call them inverse problems. And I think you have one of these problems assigned as one of your homework problems.